Here is an image showing the highest point of the path of a ball after one bounce. Someone is collecting data to model the bounce height of this ball after each bounce. Which measurement for the location of the top of the ball would be the best one to record? So if we look at A says 26 centimeters, which would be this point right here. So while we do know where 26 centimeters is, this is not the best measurement because you can see part of the ball is above it. If we look at B, it says 26.4 centimeters. Well, these little markings in between are millimeters. So we can actually count up to 26.4, and we can see that that's where the top of the ball is. So that would be an accurate measurement. If we look at choice C and D, this has an even more accurate measurement. But the ruler that is being used does not have more accurate markings. So what we want to do is measure to the most accurate marker and not estimate beyond the markings. So A is not accurate enough, and C and D are estimates. So B would be the best measurement. If you have any questions about how I answered this practice problem, please use classroom time now to ask for further clarification. Function h describes the height of a ball in inches after n bounces and is defined by the equation h of n equals 120 times 4 over 5 to the power of n. Number 1. What is h of 3 and what does it represent in this situation? So for number 1, h of 3 means you substitute 3 in for n. So we have 120 times 4 over 5 to the power of 3. Now, we can go to the calculator. 4 divided by 5 equals 0.8. And now we're going to take 0.8 to the power of 3. And that equals 0.512. And now when we multiply that by the original 120, we have 61.44. And it says that this would be the height of a ball in inches. So that would be 61.44 inches on the third bounce. So that would be just above 5 feet. Number 2. Could h of n be 150? Explain how you know. Well, if we look, 120 is our starting amount, and 4 over 5 is our growth factor. When the growth factor is less than 1, then this is exponential decay. So if the height of the ball starts at 120 inches, it will only ever be less than 120 inches. It could never be 150 inches. So no, the growth factor is less than 1, so the height decreases. Number 3. Which ball loses its height more quickly? This ball, or a tennis ball whose height in inches after n bounces is modeled by the function f, where f of n equals 50 times 5 over 9 to the power of n. To answer this question, we have to look at the growth factors. We already said 4 over 5 is equal to 0.8. So after every bounce, it maintains 80% of its height. Now we need to look at 5 over 9. 5 divided by 9 equals 0.5. We can round that to 0.6. So the first ball maintains 80% of its height each bounce. So it loses 20%. The tennis ball only maintains 60% of its bounce, so it loses 40% every time. The tennis ball loses height more quickly. So we would say the tennis ball loses height quicker because its growth factor is smaller. The smaller the growth factor, the less height it maintains on each bounce. And number 4, how many bounces would it take before the ball bounces less than 12 inches from the surface? So every time we are going to multiply by 4 over 5 or 0.8. we have already figured out that the third bounce would result in 61.44 inches. So we could make a table, and I'm going to start it with the fourth bounce. We'll say 61.44, and now we're going to multiply by 0.8. Now we're at 49.2. We're not there yet. So now let's check the fifth. We'll just multiply this by 0.8. And we're down to 39.3. We're not there yet. So now let's go to bounce 6. We're down to 31.5. So let's skip a couple and let's try 8 times 0.8 times 0.8. Now we're down to 20.1. So now let's skip a couple more and let's try 10 times 0.8 times 0.8. We're at 12.9. So it looks like one more might do the trick. So let's say times 0.8. And now we're at 10.3. So it would take 11 bounces to reach 10.3 inches and be less than 12 inches. If you have any questions about how I answered this practice problem, please use class time now to ask for clarification. After its second bounce, a ball reached a height of 80 centimeters. The rebound factor for the ball was 0.7. From approximately what height in centimeters was the ball dropped? So we don't know the starting height. So we'll call that x. We do know the growth factor. That's 0.7. And now we know we're talking about the second bounce, so we would make our exponent 2. They're telling us the height was 80 centimeters. So we would set up the function like this. Now, if I wanted x by itself, which would be the starting height, this is multiplication. X times 0.7 squared. So we're going to divide by 0.7 squared. And if we divide the right by that, we're going to divide the left by that. Now this cancels out, and what I have is x equals 80 divided by 0.7 squared. And now we can go to our calculator. We have 80 divided by, and I'm going to use the parentheses here, 0.7 squared, and close my parentheses, and then hit equal. And that's 163, which is choice D. If you have any questions about how I solved this practice problem, please use classroom time now to ask for further clarification. Which equation is most appropriate for modeling this data? So when we look, notice that we start with x equals 1. Your y-intercept is when x equals 0. So our y-intercept is not 79. 79 is when x equals 1. So B cannot be correct, and C cannot be correct. So it's either A, which is an exponential function, or it's D, which is a linear function. So now we need to see, are we adding the same amount each time? To go from 79 to 101, you add 22. To go from 101 to 124, you add 23. To go from 124 to 158, you add 34. To go from 158 to 195, you add 37. And to go from 195 to 244, you add 49. So we can see that we are not adding 22 every time, so the answer cannot be D. That means A, the exponential function with a y-intercept of 64, is the correct answer. If you have any questions about how I solved this practice problem, please use class time to ask for clarification now. The table shows the number of employees and number of active customer accounts for some different marketing companies. Would a linear or exponential model for the relationship between the number of employees and number of customers be more appropriate? So first, we're going to check if it's linear. To go from 4 to 8, we add 4. To go from 8 to 13, we add 5. To go from 13 to 17, we add 4. And to go from 17 to 39, we add 22, but that has been a jump in x of 6. So on average, we have added 3.66 per. So we do not add the same amount every time, but we are adding approximately 4 every time. Now we need to look and see if this was an exponential model. To do that, you take the second y and you divide it by the first. So here, 8 divided by 4 would be multiplying by 2. But to go from 8 to 13, 13 divided by 8 is 1.6. To go from 13 to 17, 17 divided by 13 equals 1.3. And to go from 17 to 39, that's 39 divided by 17. But that's over the span from 4 to 10, so we need to divide that by 6. That's an average of 0.4. So we are nowhere close to multiplying by the same thing every time. So this actually fits a linear model closer than it does an exponential model. Because we're closer to adding by the same amount than we are to multiplying by the same amount. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. Here are equations defining three exponential functions, f, g, and h. Which of these functions grows the least quickly? So for number one, if we want to know the rate at which they grow, we're looking at the growth factor. The bigger the growth factor, the quicker the growth. The smaller the growth factor, the slower the growth. So if we want to know which one grows the least quickly, we're comparing 3, 3.5, and 4. That means F grows least quickly because the growth factor is the smallest. Next part, which one grows the most quickly? Well, the larger the growth factor, the quicker the growth. 4 is the largest growth factor, so H grows the most quickly. Number 2. The three given graphs represent f, g, and h. Which graph corresponds to each function? Well, we just said A grows the most quickly. So A corresponds with H. And we said C grows the least quickly, or F grows the least quickly. So F corresponds to C. And finally, G is in between F and H. So B corresponds with G. And number 3, why do all three graphs share the same intersection point with the vertical axis? When you are at the vertical axis, x equals 0. So y-intercept is when x equals 0. In all three of these, when x equals 0, they all become 100 times 1. And that equals 100. Because anything to the power of 0 is 1, and anything times 1 is itself. So all three functions become 100 when x equals 0. If you have any questions about how I solved this practice problem, please use classroom time now to ask for clarification. Here are graphs of three exponential equations. Match each equation with its graph. If you notice, all three graphs have different y-intercepts, and the number by itself in each equation is the y-intercept. So, when we look at A, the y-intercept is 20. That would be at this point right here on the red line. So A must match graph M. Next, B has a y-intercept of 50. And we see that y-intercept right here at the beginning of the green line. So B must match number 2, graph L. And finally, C has a y-intercept of 100. And we see that at the beginning of the blue line. So that means C must match number 1, graph K. If you have any questions about how I solved this practice problem, please use classroom time now to ask for clarification. The function f is given by f of x equals 160 times 4/5 to the power of x. And the function g is given by g of x equals 160 times 1 over 5 to the power of x. The graph of f is labeled A, and the graph of g is labeled C. If B is the graph of h, and h is defined by h of x equals A times b to the power of x, what can you say about A and B? Explain your reasoning. So A has the same y-intercept that the other two have. So if the intercept was 160 for F and the intercept was 160 for G, then the intercept for H must also be 160. For B, we know that graph A has a growth factor of 4/5, so it keeps 4/5 of its value each time. We know that graph C for function G has a growth factor of 1/5. It only keeps 1/5 of its value each time. And we can see that B is in between those two. So we could say 1/5 is less than B, which is less than 4/5, because the growth factor is between the other growth factors. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. Here is a graph of y equals 100 times 2 to the power of x. On the same coordinate plane, number 1, sketch a graph of 50 times 2 to the power of x and label it A. So for A, we know we have a y-intercept of 50, and we know that it's going to double each time. So after 1, 50 times 2 is 100. 100 times 2 is 200. 200 times 2 is 400. And 400 times 2 is 800. And then we can connect, and this would be graph A. For number 2, sketch a graph of y equals 200 times 2 to the power of x and label it B. We know the y-intercept is 200, so we can plot the y-intercept at 200, and we know that our growth factor is 2 each time. So 200 times 2 is 400. 400 times 2 is 800. And 800 times 2 is off this coordinate plane. So we can draw the line that connects these. And this we would label as capital B. If you have any questions about how I solved this practice problem or any other practice problem from these lessons, please use class time now to ask for help. If you still have time left, you're more than welcome to go on Khan Academy and work on the illustrative math modules that cover this exponential function unit. This will give you extra practice and more help before the mid-unit test next week.